So, good morning, everyone. Today we will start with the next topic, in fact, next chapter. So, basics of digital filtering. I'll be covering this chapter from two books Principles of Linear Systems and Signals by P.P. Lati and Biomedical Digital Signal Processing, C language examples and laboratory experiments for the IBMR PC by Tompkins J. Willis. So it is one of the very say oldest and most easiest book on biomedical digital signal processing. And if you read this, you will be having an understanding about what is biomedical digital signal processing, classical biomedical digital signal processing, and what you can expect from this topic. Okay, so this book has been written in such a way, the second one, that even a person from non electronics and electrical or computer science background, they can understand the topic in a very lucid manner. Okay. So let's proceed. So the first thing is sampling. Okay. So we have already discussed about sampling. So what is sampling? If we are having a signal and we discretize the signal in the time domain, then the process of discretization, it is regarded as sampling. Okay. Now in medical industry, what is the example? In medical industry, suppose you are having a human being who is admitted in a hospital, and on his body various sensors are being attached to record his physiological parameters. Okay. Now one of the very simplest sensor is thermistor. One of the most simplest sensor is thermistor. So what is a thermistor? Thermistor is a resistor whose resistance changes with respect to change in temperature. Okay, and it helps us in the measurement of temperatures. Okay, so if you have a thermistor, so thermistor in itself, it is a, what it is? Thermistor, it is a analog temperature sensor. Okay, you will find two types of sensors, analog and digital. Both type of sensors are there, but thermistor in itself, it is an analog sensor. Okay, so as you take the signal from here, initially we will be having analog signal processing systems which will do some manipulation on the sensor. Okay, so it is basically a hardware thing. Say for example, over here you will be having some say this voltage dividers and all these things, so that you can accurately measure the voltage drop across the thermistor, and then you want to record this, and then if you want to band limit this. Okay, so all these things, it would come under the analog signal processing. Now once you have what do you call this, you have band limited the signal, then the signal is fed into a digital signal processor, where you implement the digital processes like filtering, amplification, whatever you want to do. So you do that over there. Okay, and then within the digital signal processor itself, in many processors, you will find that there is a digital to analog converter. Okay. Okay. So uh, again, sorry, I missed one step. So after analog signal processing, you will be having digital to analog, analog to digital converter, ADC. Then it will go to DSP. and within this DSP you will be having the DAC, which is digital to analog converter. It is there. Okay. Then you will be having the recording devices or the display unit. Okay, so that you can look into the mm, signal component. Say for example, whenever a patient is there in the ICU, you will find beside that ICU there is a monitor. Okay, and in this monitor you will find that you are having this ECG signals like this, and right, then you may have respiratory patterns, it would be there, then body temperature patterns would be there, then at one end you will be having the heart rate being flashed. Okay, so there are many things. So this system, it is called multi-para monitoring system. Okay, so it is multi-para monitoring system. So multi-para means, in short, they call it multi yeah, parameter. They make it in short as para. Okay, so in common language, when they are discussing, they call it as multi-para instead of multi-parameter. So multi-para monitoring system, it would be there. Okay, so which serves as the interface between the patient physiological parameters and the user. In this case, the user is the doctors and not nurses who are who are a part of the medical team. Okay. Now, what happens over here is that, suppose you are having, so I said you are collecting the temperature. Now this temperature, it varies with time. Okay, and the output of the analog signal and even the analog signal processing unit, it would be a continuous time signal. But we have already discussed that digital systems, they need digital signals. That means they should be discrete in time and their amplitude should be discretized. Amplitude discretized and quantized. Okay, then only it will become the digital signal, right? We have already discussed that. So you have the continuous time signals. Now how to make it the a discrete time signal? Initially you have to make the signal a discrete time signal. Okay, now how do you make it? You do the sampling of the system. You do the sampling of the system. Okay, now when we do the sampling of the system, we basically multiply it with delta train. Okay, which we have already discussed in one of our previous classes. So say for example, in this figure 4.1, we are having a continuous time signal which is there. Then we are multiplying with, see, some impulse inputs, impulse yeah, signal, right? So when we are multiplying this, if you see within this 0 and 1 index, the amplitude value is 0. So when you multiply the signal component with the delta at 0th instance, we get a 0. Then in the first instance of time, when we multiply the delta t, which has been delayed by 1 unit, you can say delta t minus 1, we get a of 1. Then similarly we get a of 2 and so on, right? So when we do this, then it becomes a discretized signal, and this distance between 0 to 1, it is called the time period. It is having a time period of t. Okay, so t can be 1, it can be 0.1, it can be 0.2, anything it can be. In this figure, for the sake of simplicity, it has been taken that capital T is equal to 1. Okay, now f is sampling frequency, it is equal to 1 by capital T. Okay, sampling frequency, it is 1 by capital T. Now, with this basic information that how we get the sample signal or the discretized signal, discretized signal, let's move forward into the Z domain, where we'll be later on looking into how we can design the filters and all these things. So, in the next couple of classes, I will be building you the basis of how we can design the digital filters. Then slowly we'll be moving into FIR filter and IR filters. Okay. Now, suppose we are given with a sequence xn equals to f0, ft, f2t, f of kt, which we have seen in the previous case. So this is a0, at, a2t. So if we generalize this amplitude values, so we get f0, ft, f of 2t, f of kt, right? Now, if we apply z transform over here, instead of xn, let's take it as fn. So if we take the z transform, then we get this equation f of z, which is in the complex domain. It becomes f0 into z to the power minus 0, which is equal to 1. So they have not put anything. Then ft, z to the power minus 1, f of 2t, z to the power minus 2, and so on. Okay. So in our last class, we have discussed that this equation, which we can get from the previous equation, if we generalize it, it is called unilateral Z transform. Okay, and when we talk about unilateral Z transform, we have already discussed that the unilateral Z transforms, they are related to the causal systems. In general, whatever the classical filters that are used are causal systems and are being used for biomedical applications. So the unilateral Z transform, it is one of the most important transform for analyzing conventional digital processing systems that are used for biomedical applications. Okay. Now over here, if you see what they have done, if we have this Z transform, that's literally good. So what happens now? If we further want to generalize this, it would be say AZ and all these things, and from there we can get to the more generalized function. Okay, which is again your unilateral Z transform. Now considering the previous case, suppose you are given with an input of x of n, it is equal to 1 2 5 3 0 0 0, like this. So if I ask you, you convert this signal into a Z transform equation. So what you will do? xn will become xz, which is equal to, there is no pivot, so 1 multiplied by z to the power minus 0, because n is equal to 0, 1, 2, 3 and so on. So if you see 2 into z to the power minus 1, 5 into z to the power minus 2, 3 into z to the power minus 3. Okay. Suppose this equation itself, in this equation itself, I had put a pivot at 3. So what would have been the z transform? Again, n equals to, now this would be the 0 because I have put the pivot, minus 1, minus 2, minus 3. So my x of z, it would have been 1 into z to the power minus of minus 3 plus 3 plus 2 into z square plus 5 into z plus 3. Okay. So please keep this in mind. Please keep this in mind, because when we will be solving the digital filter equations or the numericals, we will be needing these concepts over there. Okay. Now, if you see over here, there are three things in this equation, in this type of equation. Okay. So what are the three equations? The first one is the Z inverse itself. So what do you mean by Z inverse? Z inverse, it is regarded as a delay. It is regarded as a delay. And what does this delay do? This delay, it stores a number for one clock period. Okay. It stores a number for one clock period. Say for example, in every class, especially in the UG classes, you will find some one student will be there who will be holding up a student, चल आज क्लास बंक करते हैं, राइट. सो दैट पर्सन इज ए डिले, जो पकड़ के रख रहा है दूसरा बंदे को, who wants to go into the class, that person is the delay. Okay. खुद भी नहीं जाएंगे, दूसरे को भी नहीं जाने देंगे. So this is the thing. So in such a cases you will mostly find कि एक बार ही वो डिले करता है. लेकिन ऐसा अगर दो, if you find two students consecutively, पहला वाला पहले वाले क्लास में नहीं जाने दिया, next one he will again not allow the student to go to the next class, then he will be available for the third class, right? So this is the function of the delay. Delay, what it does is that it holds a number or an input for a one clock duration. That means until the next input does not enter into the system. Okay. That we will discuss in a few moments time. So what is the next operator? If you see, 2 multiplied by z inverse. So the second one is multiplier. Okay. And third one is pretty simple, if you see, plus. Okay. Which is the adder. So multiplier and adder, I feel every one of you knows what is it. You have an input, you have a multiplier. In this case it is 2. The input is getting multiplied by 2 and we get D, which is equal to C into K. Okay, in this case if we consider K equals to 2, so it would be C into 2. Right. Similarly, adder, E summation of F is G. So G is equal to E plus F. These are the adder. Adder can also be represented in this fashion. Addition sign. This summation or addition, whatever you want to do, doesn't matter. Okay. Now let us understand how this delay function it works. And for this case, we will take this equation itself. Okay. So let's say I take xn as the input, and I have made two signal flow graphs or signal flow paths in fact. Okay, the first signal, it is going in this direction, xn directly to the output. Say for example, my output is A. Second one, xn z inverse, and then we are getting the output, say it as B. Okay. So in xn, what we have at the first instance, 1. As soon as you put 1, that 1 will be available at the location A. Okay. However, as I told you that Z inverse, it is an delay and it is holding the number. So what it will do? It will hold this number at this instance. So previously what Z inverse was holding, it was having nothing. So it becomes 0, right? In the second instance, what we have in the input, we have 2. Here also instantaneously it will come over here. What will happen over here? It is already holding 1 from the previous cycle, so we get 1. Okay. Next instance, we give 5 as the input. 5, here we will get 2. Then 3, 3, 5. Then we will have 0, 0. Here we will be having 3. And then as you go on increasing, everything will be having 0, 0, 0, something like this. So do you get this now? Right? Now then, what is the next thing? Let's take an example where we are having 2 delays. A, B, C. Okay. We'll put the same numbers again. 1, 1. Here what will be having? 0. C what will be having? 2 instances back. Again 0. Then we have 2, 2, 1, 0. Then what will be having? 5, 5, 2, 1. Then we'll be having 3, 3, 5, 2. Then 0, 0, 3, 5, 0, 0, 0, 3. And again if you start giving 0, you will get 0 at all the 3 nodes. Okay. So if you see, take the case of 1, Z inverse mean after the first instance at n equals to 1, you are getting the value. When you have 2 Z inverse, then you are getting the value after 2. Okay. So I don't know whether you have seen or not, in the equation we are having Z to the power minus 2, which is basically Z inverse multiplied by Z inverse. Okay. Now herein what we have done, Z inverse followed by another Z inverse, the combination of these two is Z to the power minus 2. There is no operator for Z to the power minus 2 or Z to the power minus 3 or if you generalize z to the power minus n. We only have operator for z to the power minus 1, which is the delay. Okay. Now if you have to make implement z to the minus 5 operator or implement 5 delays, that means sequentially you have to put 5 delays into the system. Okay. Yeah. Now all of you must have understood from our last class what is aliasing. Now in the aliasing, I have told you that due to the spectral leakage, there is mixing of low frequency component with the high frequency components, right? When we are having inappropriate sampling, okay, that means the sampling, it is not following the Nyquist rate, or even if it is following the Nyquist rate, and if we are using a low cost device, even if your technically your idealistically your sampling form is okay, but what is happening is that your due to the non-idleness of many of the components, there will be some spectral leakage, and there you will be having aliasing, where aliasing means as the low frequency component, it mixes up with the high frequency component when the signals components are repeating in the frequency domain. Okay, due to the sampling of the signal in the time domain. Remember, you're having a blank face. So if you don't understand, please let me know. Okay. Otherwise, the things will be getting more and more complicated as we go forward. So again, coming back to the lecture, in the aliasing, what we'll be having, they will be mixed due to some reason. They will be mixing of the low frequency component and the high frequency component, right? Whether you do not fulfill the this Nyquist criteria, or due to the non-idleness of your behavior of your device, due to that you will be having aliasing. Okay. Now this process of anti-aliasing, that means removing the aliasing process, it cannot be implemented in any digital filter. Okay, you cannot, if a signal is corrupted due to aliasing, you cannot make it a perfect signal in the digital domain. For such kind of signals, the way to make the system what do you call, not having any not acquiring any alias signal, is that you have to increase the sampling rate. Okay, you have to increase the sampling rate. So as I told you, raising the sampling rate to twice the highest frequency present. If you do it, then only you will be able to remove the aliasing from the signals. Okay, and in the low cost devices, if there is aliasing due to the spectral leakage, then you may have to increase it to more than 2 times the maximum frequency. Okay, so that precaution you need to take. Okay. So this is in many cases not possible. Say for example, when we are using any system for say particular what do you call, a particular function, we as biomedical engineer, in most of the cases we take it as say analog to digital converter, ADC, right? So we just use it as a component and we use the system. So what happens over here then? The thing is that we do not look into the Nyquist criteria as such. We just look into the data sheet. What is the maximum frequency it can be handling and all these things. We just do it and we just plug it in. Okay. Now, what the manufacturers have done, if you see, the most digital signal processors have an analog front end, the anti-alias filter. So, if the manufacturer is saying in your data acquisition card that it can be used for a frequency up to 500 hertz, so that means it has already implemented one band limiting filter. In this case, it is basically the low pass filter. Usually, it is the low pass filter of 500 hertz, so that even if you give a signal which is having frequency greater than 500 hertz, due to that filter, your sampling, your maximum frequency of the signal will be limited, and the anti-aliasing will not happen. Okay, the anti-aliasing is on. Now the next point is very important. When we try to design any type of filter, the number of poles, it should be greater than the number of zeros in a realizable filter. In a realizable filter, the number of poles should always be greater than the number of zeros, greater than or equal to the number of zeros. इक्वल टू यहाँ पे मिस हो गया, so please greater than or equal to the number of zeros. Okay. Now coming to the most intriguing part of the digital filter design, which will clear up your concepts how the filters are working. Now in the first case, we are basically in the S plane, which is for the continuous time signals and systems. Okay, so let us understand how the filtering it happens over here, then you will be able to appreciate what happens in the digital filters. Okay, so suppose if we are having this S plane, so suppose this is an S plane, I am having a point Z in the plane, and I am having a point, another point P. Now this Z, it is a vector, this P again it is a vector. So what do you say about the distance of Z to P? So Z to P is also a vector, where Z minus P is the vector. Okay. Now what do you do with the filters? What do you do with the filters? Filters helps us to remove some unwanted frequencies. Okay, so we are mainly interested in frequency axis. Now this P, now this P, it has to be on the frequency axis. Okay, if this P is present at any point, it is having, it becomes a complex number having both real and complex things, right? Because in S plane, x-axis is real and y-axis is imaginary axis, which is basically the frequency axis. So if you put the point anywhere, then this point is having both real and the imaginary component. But we are only interested in the imaginary component because we are interested in the frequency domain. Okay, so what happens over here is that we have a point over here, say Z, and we have a point on P. The P, it has to be moved on the imaginary axis. The P has to be moved on the imaginary axis to understand the frequency behavior of the poles or the zeros. Okay. Now, what are poles and zeros? I will discuss a bit later. Okay. The poles they are usually represented by this X symbol, cross symbol, whereas the zeros they are placed they are represented by open circles. Okay, poles are represented by cross symbols, zeros are represented by open circle symbol. Okay, now there is a very interesting observation over here. If you see the poles, they are on the left hand side of the imaginary axis. Okay, whereas the zeros they are present on both the sides. They are present on both the sides. Now, what does that mean? There is a reason. So, what is the reason? The poles cannot be placed on the imaginary axis and also on the right hand side plane of the uh, S-plane. Okay, poles are always to be placed in the left hand side of the S-plane, whereas zeros can be placed anywhere. Zeros can be placed anywhere on the S-plane. Are you getting my point? Zeros can be placed anywhere on the plane, and poles can be placed only on the left hand side. Okay. Now herein, if you see there is a term h of s, we have called it as transfer function. Now, what is a transfer function? If you remember correctly, if we take the example of say non-inverting amplifier, V0, sorry, V in, V out. So V0 equals to, this is R2, R1. I hope everyone knows this circuit, whether from biotech or biomedical, doesn't matter. So we get 1 plus R2 by R1 into V in. Okay. So basically A equals to 1 plus R2 by R1. Now why this is so? This is so because if you look into the resistances, they are frequency independent. So the gain over here is frequency independent. Okay. On the contrary, when we talk about Hs, which is basically the transfer function, this S is related to the complex number or the complex domain, and this complex component it is associated with the frequency, right? It is associated with the frequency. So instead of this R and R1 and R2, if we place some capacitance or inductance, capacitor or inductor, so what it will do, these R1 and R2 it will be changed to Z1 and Z2, right? So this same circuit it would become frequency specific circuit. Okay, so in that case our gain it is equal to 1 plus Z2 by Z1, but this gain was used for the frequency independent behavior. Now we have included frequency dependence, so it is basically h of s. Okay, it is basically h of s. Now this h of s is the transfer function of this non-inverting amplifier which is having capacitor and inductor into its circuit. Okay. Now the thing is that now the over here what we have is that, so what we understood from here is that transfer function is nothing but a gain factor, or in other words we can say frequency dependent gain factor of any given system. Okay, of any given system. Now, okay, now this HS, it is basically a, it is having basically two polynomials, okay, which is PS by PQ, PS by PQ. HS, it can be represented in the form of PS by PQ. Okay, now when I am talking about polynomial, what we have, it will be having several roots. It will be having several roots. So if you see the polynomial in the numerator, we have put several roots. Similarly, for Q of S, we will be having several roots, and we have put the equation in this factor so that we can identify the roots in a specific way. Apart from this, there is one constant. There is one constant Bn. Now, what is this constant? This constant is the frequency independent constant. As in, say A equals to R2 by R1. If frequency independent, we are having frequency independent gain. So this B, it is also again basically, but that gain is frequency independent. And when we have the frequency independence, when, if you look over here, in the DC component, whatever will be your at the DC frequency, whatever will be your gain, that will be your frequency independent gain. Okay, so this Bn, which is basically a constant, it is due to that frequency independent behavior of the DC frequency, of the DC component. Now the next thing is that, suppose we are in the S plane, so we are having S minus Z1. So if we put it equal to 0, so we get a solution of S equal to Z1. Okay, so when S is equal to Z1, what happens if I put this value over here? What will happen? It will bring down this PS to 0. Okay, because this PS equal to be 0, so what will be happening to the HS? HS will also be 0. So the solutions of the numerator polynomial, they are regarded as zeros of the system. Similarly, if you find out the solutions of the denominator, and if you put the value, say for example in the first case S minus lambda 1, if you put lambda 1 S equal to lambda 1 and we put it, the QS will become 0, and when the QS becomes 0, what will happen? HS becomes infinity. HS becomes infinity. Infinity means, if I am standing it and if I try to put something of infinity here, so it will, I will be having an infinite pole or something like that, right? So this putting up a pole which is having infinite what do you call infinite amplitude, so the effect what we'll be having is that of a pole. Okay, so compared to is, say for example, compared to an ant, if you are having an ant, okay, my drawing is very bad, so bear with me. So if I put a pole over here, so what you will be having, this ant will see that this pole is infinite in length. So this, from here this name comes poles. So the solutions of the denominator, it is regarded as poles, whereas the solutions of the numerator, it is regarded as zeros. Okay. So what are these poles over here in the diagram? Now you can really appreciate, right? What are these? These are the solutions of the zeros. They are the solutions of the polynomial of the numerator of the transfer function, whereas these poles, they are the solutions of the denominator of the transfer function. Okay. So this is what it has been written over here. S equals to P, if you put, so you get equation like this. Now again, that was in the rectangular coordinate. In the polar coordinate, if you try to put that, so you will be having r1 e to the power j phi 1 phi 2. So what are these phi? These are the phase angles, and this r1 r2, what are these? These are the this distance value z to p. But this p, I have told you that we have moved it onto the imaginary axis for our for designing the filters, right? So from the point of zeros to a particular frequency axis. Okay. So if you are having different R1, R2, we will be having the different values of R1 and R2 from different locations. So from here, say from 0, 1, if I put a radius to the frequency axis, at this point I will be having, say, R1. From here to here, at the same point I will be having R2. Okay. Similarly, at the same point, if I have this one, the distance between this and the frequency axis is, say, P1. From here to here, we will be having P2. Okay. So we get that. If we now take out the real components, and if we combine the imaginary components separately, what we get? The modulus of h of s is bn into r1 into r2 to rn, then d1 d2 dn, which is nothing but product of the distances of 0 to p and product of the distance of poles to the point p. Okay. And the phase angle at p, it is given by phi 1 plus phi 2 plus phi n minus of theta 1 plus theta 2 plus theta n. Okay. Theta 1 is at the bottom. So sum of 0 angles to P minus of sum of 0 pole angles to P. Okay. Now if you see, we have done this for a single point, and when you want to find out the HS in the different frequency point, so we have to start from the DC frequency. Initially the DC frequency will be your first frequency, then you will increase, you will get the next frequency point, then you will get the next frequency point, like this. So you have to take, say, if I say it as P0, P1, P2, so you have to take all the values from P0 to P infinite to get the actual frequency response of your system. Okay. So I have given, it has shown you for a particular P point, but this P point itself is varying. To get a clear picture, what is the output of your filter, you have to take this filter activity from DC frequency to the infinite frequency. Okay. So I think we are, yeah, only 5 minutes are left, so I will stop over here. So if you have any questions, we can discuss. BN, see, BN over here, if you see R1 e to the power j phi 1, what is what you are having? R1 is the real component, this phi 1 is this thing. So everything is associated with some phase. Okay. In Bn, if you see, it is a constant. Okay. It is a constant. So which is regarded as the constant gain of the circuit, and it is frequency independent. That's why if you see phi 1, phi 2, when you say that it is dependent on the frequency or not, at all the frequencies it will be having the same value. This is just like a constant. So we call it DC gain. Just like in the previous case, A equals to 1 plus R2 by R1. At all the frequencies, the gain would be the same, R2 and R1. The phase components only comes when we include the capacitor and the inductor. So that would vary with the frequency. The gain of that, if you include the capacitor and the inductor into the system, the gain would then be varying with the frequency.